This research is called Cortical Information Processing for Anticipation and Surprise. And the field in which this research takes place is called physics of cognition. That is literally an intersection between physics and neuroscience. And the most physics part, I would say, is in the coding, and the cognition part is the neuroscience part coming from psychologists and other neuroscientists. Just to get started a little bit, the main topic of this research is called multisensory integration. Literally is what we experience every day. So we have different stimuli coming from the external environment, and it's the process of our neurons and our brain putting them all together to create a unique perception. So the research question that we wanted to answer that sees as multisensory integration is protagonist is whether we can understand before something happens what the brain expects from it. Just imagine there is a distance between these stimuli, and then you want to understand what the brain thinks in this region between the two stimuli. Is it going to expect the other stimuli? Is it not going to expect it? How much information does the brain get just from waiting between these two stimuli? EEG is also known in this extended version as electroencephalogram, and is a test that measures the electrical activity in our brain by measuring the stimuli and action potentials. And the whole EEG technique is based on this principle called principle of differential amplification, meaning that we have two electrodes that are on two different positions of our head, but not too far apart. And we have one of them exactly in the region we want to measure, and the other one that is in a reference position. And what we're doing is literally subtracting the value between the one in the region we want and the one that is a reference. And this difference in electricity, this voltage, actually differences between the two electrodes, is what the EEG measures and what the EEG creates a spike of. These spikes are just millions of neuron spikes adding together. All in a nutshell, we have these people and we measure the EEG activity, and we give them two diverse type of stimuli, an auditory stimuli and a tactile stimuli. And we saw what happens between the moment I give an auditory stimuli and the moment I give the tactile stimuli in these people's brain. But the four conditions are created so that the first type is called no tactile, and we just have the auditory stimuli, and then nothing happens. So that's the first set of trials. The second set of trials is called 100% expected. So we have the auditory stimuli here, and then after 500 milliseconds, we have the tactile stimuli here. Then we have the other type of condition that is the time uncertain, where we have auditory stimuli here, and then we have tactile stimuli here after 220 milliseconds, or you can have it after 500 milliseconds. So the people that are subjected in this experiment don't really know which, when are they gonna get the tactile stimuli. The last one, we have 50% chance. So we have the auditory stimuli, but you don't know if you're gonna get the tactile stimuli because it takes two different variables that are X and Y. And it wants to understand how much, just by looking at Y or by looking at X, I can understand about Y or X. How much I can understand just by looking at one channel of the temporal cortex about one channel of the tactile cortex. And to do that, we use a tool that was created by Dr. Eslam Abdelaleem, and he called this the Deep Learning Estimator or Neural MI library. And what he did is creating a neural network where he embedded this loss function. And the loss function, as the term actually says, indicates how much information was lost by something. So you want to minimize the loss function so that you can understand as much as possible by X just by looking at Y and vice versa. You can think about bits as quantities of information. So one bit, one piece of information, two bits, two pieces of information. We see the no tactile, we have just the auditory stimuli. So you can think of the brain just as asking you, is there gonna be a tactile stimuli? The brain is in this frangent, in this time between the auditory and the tactile stimuli, is asking itself, is there gonna be a tactile stimuli after the auditory one? The no tactile had one bit of information. What a bit of information because it was only one question. So you can imagine bits of information as questions. In the second case, we have 100% expected. And we have the auditory stimuli and the tactile stimuli. However, as you can see here, in this second condition, after the auditory stimuli, you always have the tactile stimuli. So in this case, the brain is asking itself, will I get the tactile stimuli? Yes or no. Will I get the auditory stimuli? Yes or no. So you would think there are two questions here to be asked. However, After a while, in these 60 trials, so already after 5 trials, the brain has started thinking, okay, after every auditory stimuli, I will also get the tactile one. So even if I ask just a question about the auditory, I will automatically know what happens in the tactile and vice versa. So actually, the brain is not asking, do I get the auditory, do I get the tactile? It's just asking, do I get the auditory or do I get the tactile? So also in this case, as we saw in our previous results, we have in the 100% expected just roughly one bit of information. However, in the other two conditions, we don't know when the tactile is gonna come. So in the third case, is gonna be I have the auditory stimulus, and the brain is gonna ask, will I get the tactile stimulus, and when? So in this case, the brain is asking two questions, and just by looking in the auditory, just by asking about the auditory, it will not know which one of the two tactile is gonna get. And same thing, I could ask already about the tactile, but I don't know about which tactile to ask. So either way, you need two questions because there are two different timings you need to consider. And lastly, the final one is probably the one that is more obvious because at this point you don't even know if you're gonna get the tactile, so you need to ask two questions. All in all, you always need to think of the brain as a system of bits of information where each bit is actually a question that the brain asks to understand what is going to happen next. So we understand that the brain wants to make measures fast and efficiently. That the brain measures in a quantitative way, and in these bits, they're always going to be the same and gonna add up or be scaled down. Why didn't we choose any other method but mutual information? The reason why we did this is because, as you can imagine, the brain is not an easy system. It's pretty complex and it does not measure in a linear way. So a correlation, that is what is usually used in statistics, it tells you, okay, you have X and here you have Y, and this is your straight line. A linear correlation such as X and Y cannot work. It would just be too difficult to find something that is so strictly correlated. So mutual information allows us to find any type of correlation and relationship between two different variables. Because we said, okay, how much do I know just by looking at auditory about tactile? But if this relationship between or auditory and tactile is not linear, then how are you going to measure it? With mutual information. Thank you so much for listening. If you have any questions, I think we have kind of 5 minutes for it. And yes, so if you have any clarifications or questions you want to ask, please do so. Thank you.